So, we want to take a look at some of the effects of intermolecular forces on the actual macroscopic properties of the behavior of our molecules and compounds. So, there's a couple of rules you have to learn, and these rules you have to learn off by heart because we use them as reasoning behind our answers to some of our more difficult problems when we're dealing with intermolecular forces. So the first one that they talk about there is substances with weaker intermolecular forces evaporate faster than substances with stronger intermolecular forces. Now, a very easy way to think about this, if you think, for instance, about something like nail polish remover, okay? As soon as you open up a container of nail polish remover, it doesn't take very long before you smell it everywhere. That's because the actual acetone in the nail polish remover has got a very weak intermolecular force, so it evaporates a lot faster. Whereas something like water has a much stronger intermolecular force and takes more time to evaporate. The next rule then, substances with stronger intermolecular forces will generally have a greater surface tension than substances with weaker intermolecular forces. Now, probably one of the easiest ways to take a look at this is by going and taking a small drop of the substance and putting it on the surface. If we take water, for instance, it will form a perfect little round drop, where if we take something like alcohol or something like even perfume, which is alcohol based, it doesn't form a round drop, it kind of makes a splatter on the surface. That's because the actual tension holding the liquid together isn't there. It's too weak. The mass of the molecules pushes it out. Whereas in water, the hydrogen bonds are incredibly strong and keeps this molecule together. Another very easy way to take a look at surface tension is to take or think about, for instance, our little lizards that we have that can run on water, mosquitoes that can land on water, because the surface tension of the water is strong enough to actually carry their mass. Now, the next rule, substances will dissolve in solvents that have a similar intermolecular force, or solvents where the ionic bonds can be disrupted by forming ion dipole force. Now, this is actually a very easy rule. Like dissolves in like. So polar substances will dissolve in polar substances, and non-polar will dissolve in non-polar. But when we get to ionic substances love to dissolve into polar substances because the polar substances are strong enough to take the ionic compound into solution. And we have our next rule, substances with strong intermolecular forces have a higher boiling point than substances with weaker intermolecular forces. And this is not just boiling point, it's also melting point. That means the stronger the intermolecular force, the more energy we need to add to break the actual bonds between the particles to get it to undergo a phase change. Next then, substances with stronger intermolecular forces will travel further up a narrow tube. In other words, they will have a greater capillarity than substances with weaker intermolecular forces. One of the best examples of this is if you're sitting in a restaurant or at home with a straw in your cool jar. And if you take a look at the liquid in the straw is higher than the liquid in the glass. And the reason for this is because of two other forces we find, adhesion and cohesion forces. The adhesion forces is the force that makes the liquid stick to the inside of the straw. So it's the force between the liquid and the sides of the straw. Okay? And this force is trying to pull the liquid towards it, so therefore it's pulling it a little bit up. The cohesion forces is the force in the liquid, so in other words, the intermolecular force. If the cohesion forces, the intermolecular forces, is strong, that means it will want to keep all its particles further up together. So as the adhesion forces is pulling up on the sides of the straw, the cohesion force is trying to keep everything together, and therefore the liquid is drawn out the straw. Now, the intermolecular forces, macroscopic properties, affect the the intermolecular forces microscopic properties affects the macroscopic behavior of the substances. Okay. One of the other ones we can take a look at then is molecular size. Now, alkanes are a group of organic compounds. And what's very, very important to understand about alkanes is that they're little organic molecules that exist out of long chains of carbon atoms. So here in the diagrams at the bottom, the little black circle indicates a carbon atom, the little white circles indicates the hydrogen atoms that bond around it. And remember, every single carbon atom can form 4 bonds. So alkanes will go from a single carbon atom molecule, like the one here, methane, that we've worked with a lot, to 2 carbon atoms, ethane, and then on to 3 and 4 and 5, like this one we have here, or pentane, and over to 6 carbon atoms, like the one we have here, or hexane, and then even further on to something like icosane, this massive molecule at the bottom. Now, the reason we want to take a look at molecular size is because of the following. As the molecular mass increases, we see an increase in the amount of energy we need to add because the melting and the boiling point gets larger. Okay? Now, this is because of the size of those molecules. And because of the fact that the larger the molecule is, the more spaces there is for London forces to occur. So if we go back to the previous slide, we can see that here we will find that if we compare icosane to, let's say, pentane, every single one of these spots could be a spot for London forces to occur, which means that our molecule has multiple London forces, therefore the sum total of the London forces is a lot stronger. The next one then, viscosity. So, viscosity is the resistance to flow of a liquid. And if we compare at the bottom here water to syrup, then we know it's a lot easier to stir water than it is to stir syrup. Even if we take the glass of water and throw it out, the water flows out a lot easier compared to the syrup. Okay? Now, if we then take a look at the intermolecular forces, yes, water has incredibly strong intermolecular forces, but syrup is an organic molecule, and it's got multiples, a lot of London forces between every single molecule. So therefore, the sum total of all the molecular forces together is a lot stronger, and that's why it's a lot thicker. So the stronger the intermolecular forces, the more viscous the substance will be, the more difficult it will be for the substance to flow. Then we have density. Now, density is something you guys did in grade 9 and 8 technology, where we learned that density is the mass of a substance per unit volume. Okay? And this is usually mass in kilograms and volume in cubic decimeters. So if we look at something like a cork and a rock, and we say the cork and the rock has exactly the same size, then the cork would float in water, but the rock would sink. Now, why is that? The forces keeping the particles of the rock together is a lot stronger, meaning the particles are a lot closer to each other. Meaning in the same volume, we get more particles per unit volume compared to the cork. That means that at that moment, the density of the rock is higher, meaning the rock is heavier, so it sinks. Whereas the same volume, the same space, the cork has got less particles, they're further apart, and therefore it floats. Now, why does it float on water? If we look at the diagram on the right, if we take the liquids that we've got here, we've got oil, water, and syrup. Now, syrup is our most dense substance, and water is in the middle, and oil is our less dense substance. So if we just throw all 3 liquids into a glass and we shake them up and we give it time to sit, then the syrup will sink to the bottom, the oil will move to the top, and the water will stay in the middle. And this is just because the syrup is the most dense material, water is a little bit less dense, and oil has got the lowest density of the 3 of them. If we throw a cork into this glass, the cork will float on top because it's got the lowest density of all of these substances. we throw a Lego block into this, the Lego block will sink through the oil but will float on the water. And that's because the Lego block is more dense than the oil, so it sinks through the oil, but it's less dense than the water, so it floats on top of the water. If we throw a grape into it, it will sink through the oil, through the water, because it's more dense than both those liquids, but it's less dense than the syrup, so it will float on the syrup. Then we have to take a look again at melting and boiling point. Now, a very, very simple rule, and you'll remember this graph at the bottom here from grade 10, where we see our energy that we have to increase over time to actually get material to go from a solid to a liquid to a gas. Now, simple rule. If the intermolecular forces are strong, more energy is required to make the substance undergo phase changes. So our rule is, the stronger the intermolecular forces, the higher the melting and the boiling point will be. Then we have two exceptions here that I just want us to take a look at. Intermolecular forces do play a role here. We have thermal expansion and thermal conductivity. Now, what is thermal expansion? Now, you'll probably have lied in your bed late at night, and then you hear squeaking sounds in the roof, and you get scared because you think there's a big scary monster in the roof. No, it's just the house settling. Okay? Now, what does that mean? During the day, the house is in the sunlight, meaning it's absorbing energy. The roof tiles, the bricks, the mortar, everything is absorbing energy. And when materials absorb energy, the particles start moving a little bit faster, and they start pushing each other away a little bit. So the material expands. Okay? Now, as the material expands, we don't really hear those sounds during the day because, well, during the day it's loud. There's cars driving around, there's people outside, your mom is calling you to come eat breakfast. So it's a lot of other sounds kind of buffering out the sound of the expansion. But at night, when it's quiet and it's cold outside, the house starts giving that energy that it absorbed during the day off to its environment. And because it's giving that energy off, the material is shrinking. Now, those weird sounds you hear when you're lying in bed is literally the roof tiles and the roof beams and the bricks and everything scraping against each other as the house shrinks again. Now, please, this does not mean that you're going to go from a one-bedroom to a two-bedroom house, okay? The expansion that we're talking about is very, very small, and we don't really even see it with our naked eye. Now, thermal expansion can also cause quite a lot of problems for us. And if you drive over a bridge again, you'll see there's these little gaps on bridges. And even if you look at your tiled floors, there's little gaps between tiles that we leave. It's because as the material heats up and expands, the tiles can actually push against each other. And if we don't leave those little expansion gaps, the tiles can exert so much force on each other that the tile might pop out, that it might crack, that the tiles might fall off of the wall. The next one then is thermal conductivity. Now, different materials conduct heat differently, and it explains why metals get extremely hot very fast, but wood does not. It also explains why we use metals in our pots and pans and not ice or wood or anything like that. Now, metals have this wonderful thing where if we exert heat on one end, it will literally give energy to those particles, and those particles start vibrating and transferring the energy to all the particles around them. So if you've ever sat at the fire while you are frying and you played in the fire with a metal poker, then after a while the end you're holding actually gets warm. And this is because the energy from the fire is literally being expanded up through the pipe all the way to your